So let's remember a few things about solubility, and then we can see how approaching solubility equilibrium problems really uses a lot of the same techniques as any other general equilibrium problem. So the solubility of any substance is the equilibrium concentration. It is the amount of substance that will dissolve in a specific volume of solvent at a particular temperature. So in fact, there are lots of different solubilities for a compound, because if I'm trying to dissolve it in a larger amount of solvent, more solute will dissolve. And if I heat the solvent so that the molecules have more energy to dissociate the solvent, we will also see more dissolving. So for example, I could say that the solubility of silver chloride in water at a particular temperature is 0.0018 grams per liter, or 1.3 times 10 to the minus 5 moles per liter, or molarity. For a slightly soluble compound, the solubility is the equilibrium concentration. It's the E line of a rice table. And of course, most but not all solid solubilities do increase with temperature. And we can think about equilibrium and Le Chatelier's principle to think about the things that would possibly be exceptions to that. So in the video from last week's review, we saw these solubility curves, just to remind you of what's going on here. On the line here, so say for example, if I am at 30 degrees, it would take 95-ish grams of sodium nitrate to reach a saturated solution, because the saturated solution is right on the line. If I want the areas that are unsaturated or supersaturated, unsaturated would be less solute than full at a given temperature. So if it was less solute than needed, it would be below the line, fewer grams. And if it were supersaturated and it had an abnormally large amount of solute, then that would be above. A supersaturated solution at 30°C might have 100 grams in it. So let's think a little bit about the equilibrium situations we're looking at. Most salts, of course, will dissociate into their separate ions when they dissolve. The equilibrium then has the solid salt as the reactant and the solvated ions as the product. So for example, lead sulfate would form a lead ion that is aqueous and a separate sulfate ion, which is aqueous. And then we could just write a mass action equilibrium expression using the same rules that we've been using. Products over reactants, but of course there aren't any solids in the K expression, which means it's going to be simpler than some K expressions. We'll just have the concentration of the lead 2+ ion and the concentration of the sulfate ion. Both are raised to the first power because there's only one lead and one sulfate. So just remember, always, 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 no solids and no pure liquids in K. So we could get some solubility information in one of two forms. We could just get it directly as the solubility, the grams per liter or moles per liter at equilibrium. Or we might get the solubility product, what we call KSP. And both of those are coming from the equilibrium concentration. So the solubility product constant, KSP, is just a K expression. It's an equilibrium constant. The only difference is that it is specifically talking about a dissolution. So we're looking at the concentration of ions in a saturated or equilibrium solution. And that means that since K does not change unless we change the temperature, there is one KSP for a given solid at a given temperature. The solubility of the solid is the amount that dissolves, the molarity or the concentration. And that is going to have specific amounts or temperatures. So there's really kind of an infinite number of possible values. And it can be dependent on some other conditions, like the presence of a common ion, like we saw in our Le Chatelier lab. We had a saturated solution. It was full. It was on the line of sodium chloride. When we added the common ion, we saw that less of that solid was able to be dissolved because it crystallized out as a solid. So we actually decreased the solubility, the equilibrium concentration. We did not, however, change the KSP of sodium chloride. So let's look at these problems from a couple of different angles. So I could be given the equilibrium constant and be asked to calculate the concentrations. And so this is a place where we could use rice tables. We have the stoichiometry. We could figure out the change needed to reach equilibrium. And one thing we can think about sometimes is that we can sometimes simplify equilibrium problems when K is very, very small, like 10 to the minus 3 or less, by assuming that the change could be negligible when compared to a bigger number. So let's try a rice table here. We need the reaction. The reaction is going to take solid copper iodate, and it will form one copper ion and two separate floating dissociated solvated iodate ions. And so if we look at the initial, well, initially we just have water, so we would not have any of the copper ions or any of the iodate ions. And in fact, we don't really care that much about the initial concentration of copper iodate because it's a solid, so it's not going to show up in K anyway. So a little of that solid would dissociate. That would make some product. So it would make, say, X of the copper, but it would make 2X of the iodate. Because remember, we get twice as many iodate ions as we do copper because of the formula of the salt. So at equilibrium, I still don't really care about the solid because it's not in the K expression. I would have X of the copper ion and 2X of the iodate. And I mean, look at that tiny K value. That X is really small. But this is not a case where I would simplify by assuming that this is negligible, because anything is bigger than 0. We know we're going to have to shift to make some products because our starting Q value was 0. And our KSP isn't very big, but it's still bigger than nothing. So let's take the K expression and see what we can do with it. We have our reaction. So the K expression would just be the copper concentration and the iodate concentration. The iodate concentration, though, would be squared because there are 2 of them. Well, now we know that KSP is going to be equal to X and 2X squared from our rice table. So that means that that would be 4X cubed if I simplify it. Please don't forget that if it is 2X squared, I have to square the 2 and the X. It's not 2X squared, it's 4X squared. Plus times the extra X here gets me 4X cubed. So I could put in my KSP number. I would divide that by 4. And then I find that that is the concentration of the copper ion cubed. So I could take the cube root of that. If I take the cube root of that, I find that it's 3.3 times 10 to the minus third, and this is all KSP is in concentration, so this would be a molarity. Now the thing to think about here is that since there is one copper ion in copper iodate, then the concentration of the copper ion is the same as the amount of copper iodate that dissolved, because it's a one-to-one relationship. So I could use KSP to calculate the equilibrium concentrations. I could also go the other way. I could take the solubility, something say in grams and milliliters, and I could take that to find the KSP. But the K expression is in molarity. So the first thing I'm going to have to do is calculate the molarity from this mass, and then I can use the K expression and solve for that. So I am not going to add up all of the ions in lead iodate. It is about 557 milligrams per millimole. So if I take that 896 milligrams, I would divide that, 8.96 milligrams, and divide that by 557. That's going to be a very small number of millimoles, which I would divide by my 400 milliliters, because millimoles over milliliters is molarity. And I get that that's about 4.02 times 10 to the minus 5 molar. This is clearly not a very soluble salt. So I write out my dissolving expression, which always starts with a solid and forms the dissociated ions. So let's think about what would happen here. This many moles are going to dissolve. So the concentration of lead, since there's one lead to the lead iodate, would end up being 4.02 times 10 to the minus fifth. This concentration would be twice that squared. So I would just plug that in to these spots. I don't really need to find it to solve for x. I know what x is already. So the lead concentration is the same as the solubility. The iodate concentration would be twice the lead, and then I just square that. That's just a matter of plugging it into a calculator to get 2.59 times 10 to the minus 13th. And since this is a K expression, we can write that as a unitless number, assuming that the activity is the same as the molarity in a dilute solution. So here's one more. I have the solubility of bismuth sulfide. I would like to find the KSP. So of course, I'm going to need to start with writing the equation and writing the K expression. And really, honestly, it only takes just a second or two to write out this dissolution expression. And I really think that it is so important to keep you from making little mistakes. So if I start by writing the equilibrium expression, one thing it's going to do is it's going to make me remember that this is going to be 2 times the solubility. And this is going to be 3 times the solubility, because the solubility is each one of these bismuth sulfides. Then I can write the K expression. That will help me remember that I need to square this and cube the sulfide concentration, which is something that I see from writing the equation out. See what I mean? Write the equation. No ions are present initially, so the equilibrium ion concentrations are going to be the solubility times 2. because each one of these dissolving gets me 2 bismuth ions. And the sulfide concentration would be the solubility, because each one of these times 3, because each one gets me 3. Now that I have the concentrations, I can just plug that into the KSP expression and do the math. So if I plug that in, plug the concentrations in, square this one, cube that one, and I get this extremely tiny KSP. So the other thing that you can work on today is the worksheet that I am going to post on Classroom. It is to practice using a few things. One, using solubility rules like the ones on the back of the star chart. You can Google Texas star chart and get this on your computer to look for the things which are soluble or not soluble or slightly soluble. And the other part of it is to practice predicting some precipitation. So we've got both sides of the coin to practice and keep getting ready for our new material to come.